Yes, example number 3. The equation of a body performing simple harmonic motion is given by d squared x over dt squared plus 4x is equals to 0. Given that when t is equals to 0, x is 5 and the x over dt is 0. Solve for x using the d operator. Now, how do we solve for x using the d operator? Now, if you look at this equation, you are differentiating x with respect to t. When you are differentiating x with respect to t, it simply implies x is a function of t, isn't it? X is a function of t. So, you start using the d operator, meaning you let d with respect to t to be d. That will imply d squared over dt squared will be d squared, isn't it? So when we do substitution in our equation, d squared over dt squared will be capital D squared, then it is of x, isn't it? Then we have plus 4x to be equals to 0. Are we together? So after that, you let d to be m. So if you have d squared, that is going to be m squared x plus 4x to be equals to 0. Having done that, x is a common factor. So if you factorize x outside, we remain with m squared plus 4 to be 0. So when a product of two factors is 0, then it implies either the first factor is 0 or the second factor is 0. So here it means either x is equals to 0 or m squared plus 4 is equals to 0. Now, when x is 0, it means our differential equation does not exist. So when we take the second equation, which now becomes our auxiliary equation, isn't it? Our auxiliary equation. So the auxiliary equation there is quadratic, so you can see there you have m squared is equals to negative 4. If you take for the other side, because we only have two terms, you can easily get m, isn't it? You look for the square root on both sides of the equation. So there you will get m to be square root of negative 1 times square root of 4, isn't it? Because we have here square root of negative 4. Is that okay?
Yes.
So after that, you get m to be square root of negative 1 is j, square root of 4 is plus or minus 2. So it means we only have the imaginary solution. So we said when you have only imaginary solution plus or minus beta j, then your solution of the differential equation x was a function of t, meaning x is going to be what? A cos beta t plus b sin beta t, isn't it? Are we together? Good. Now from there, you now see where there is beta, you put the value of beta. When your solution is only imaginary, then this is the final solution because x is a function of t, meaning x is in terms of t, isn't it? Yeah. Are we together? Yes. So can you now put the value of beta? Beta is 2, isn't it? Yes. Beta is 2, so it means x is a cos 2t plus b sin 2. Sin 2t. Okay? Yes. Now after that you get, this is now the general solution. Now we now need the particular solution given this boundary condition, all those initial conditions, isn't it? So for us to get those initial conditions, it means we have to differentiate x with respect to t for us to get two simultaneous equations, isn't it? So if you differentiate x with respect to t, you get dx over dt to be, differentiating cos 2t, you get minus 2 sin 2t, isn't it? You differentiate cos 2t, you get negative sin 2t, you differentiate 2t, you get 2. Then you express the product of the inner derivative and the outer derivative, isn't it? Are we together? Yes. So there you end up with minus 2a sin 2t. If you differentiate and 2t, you get cos 2t, then you differentiate the inner function 2t, you get 2, isn't it? So it is going to be 2 cos 2t. Then if you multiply with your plus b, you get plus 2b cos 2t. Then now these are now simultaneous. Equation 1, equation 2. Are we together? So when t is 0, x is 5, and dx over dt is 0. So if you start with the first equation, we only have x and t. So in the first equation, where there is t, we put 0. Where there is x, we put 5 in the first equation, isn't it? So where there is x, you put 5 to be equals to t is 0. So you have cos 0 sin 0, isn't it? You know sin 0 is 0, isn't it? So the whole of this term will go to 0. Then cos 0 is 1, meaning here you remain with. So in the first equation, we found a to be equals to 5. Are we together? Are we together?
Yes.
In the first? See, we have a cos 0 because t is 0. When you put here cos 0 is 1, so you remain with a. Then it is plus b sin 0. Sin 0 is 0, so b times 0 is 0. So it means on this side of the equation, you don't remain with a to be equals to x, but x was 5. Initial conditions. Can you see? So from the first equation, we found the value of a. Then in the second equation, where there is dx over dt, we put 0. Is that okay? Yes. So dx over dt is 0 to be equals to minus 2. Where there is t, you put 0. So look here. When t is 0 sin 0, meaning the whole of this term will go to 0 because sin 0 is 0, isn't it? Yes. So 0 times negative 2a, the whole of this will go to 0. Are we together? Yes. Then here, cos 0 is 1, meaning you remain with plus 2b, which is just 2b, isn't it? Yes. So this one is equals to 2b. So if 2b is equals to 0, see that is clear that b is 0. You divide both sides by 2. So you found the value of b is 0, the value of a to be 5. So what was your equation? Your equation was this. This was your equation, the solution, the particular solution, isn't it? This was your particular. So the particular solution will now, given the initial conditions, so particular solution given these initial conditions will be what? Where there is a, you put the value of a which is 5. Where there is b, you put the value of b which is 0. So it means the whole of this term will go to 0. Here you remain with 5 cos. Was this actually the particular solution? It is this down now and where we've already substituted the value of beta, isn't it? This down equation, isn't it? So where there is a, you put the value of a which is 5 cos 2t. Then b is 0, the whole of that goes to 0. So your final solution of the second order homogeneous ordinary differential equation is x is equals to 5 cos 2t. Are we together? Very good.